Well, we're going to take the carrying capacity, we'll subtract off the number of jackrabbits and the number of cottontails, and that'll tell us how much the carrying capacity is left. Because that's not going to work, because these aren't equivalent to those in terms of resource usage. Maybe they use more of this but less of that, right? So we've got to figure out a way of converting these into an equivalent number of those. So in other words, how many cottontails does it take to make one jackrabbit in terms of resource use?
Oh, so you're going to find the amount of N1 using N2 to subtract.
Yeah, sort of like that.
Okay.
So we're just going to cheat and make it easy here. We're going to put in a variable there.
Convert N2
called-
into N1.
Alpha is called the coefficient of competition. Basically a conversion factor. So it's usually not this simple, but let's just simplify it and say, let's imagine that it takes, in terms of carrying capacity, that it takes 2 cottontails to equal 1 jackrabbit in terms of the jackrabbit's carrying capacity. So every time 2 cottontails are born, that's 1 less jackrabbit the environment can support. Okay? So in that case, alpha would be 2, because we're saying that essentially 2 cottontails is equivalent to 1 jackrabbit. Now it's probably not that simple. The numbers are probably going to be more complex to come through than that, but that's the way to think about it. And we're not actually going to calculate alpha, because you'd have to do a whole bunch of field work to figure that out. But that's the equation. We're going to convert these to an equivalent number of those, and so now really we're saying we're taking our carrying capacity minus the number of jackrabbits minus the number of cottontails converted to jackrabbits for resource use from carrying capacity, and then divide it by the carrying capacity. Okay? This makes sense? Alyssa, you okay with this?
What?
All right. So let's do the same thing for species 2. They have an R value, they have a population size, they have a carrying capacity. Your book uses alpha again with some numbers. But back in the good old days when I learned it, we learned it as beta. And I think it's less confusing. So beta, just like this. Alpha and beta are coefficients of competition. So alpha converts species 2 into an equivalent number of 1. Beta converts species 1 into an equivalent number of 2. Now your book does something like this. It's got alpha 1, 2, and alpha 2, 1. I think this is the same as our alpha, and this is the same as our beta, I think. But it always confuses me. So that's one thing I don't like. I like this book, but I don't like that. So we'll do alpha and beta, less confusing. Okay?
I could use alpha and alpha inverse instead of beta.
No, because beta is not always the inverse of alpha. Because the carrying capacities are different and the resource usage is different, they aren't, one species may affect the other more than vice versa.
So they're the same, I think.
Oh, no, sorry, that's supposed to be 2. All right, now is where the fun begins.
Chromosomes are happening there
Yeah,
before.
this is the fun zone.
Step into the bone zone. Oh wait, that was. I don't know. Those game grumps.
No, it really did not look okay in the video.
You
Huh?
did not look okay in the video at all.
What do you mean?
You're like just talking to yourself, like looking off.
Alright, so now we wanna see what these equations predict. What are the possible outcomes for these two equations? In other words, if these two species compete for some period of time, what could happen, right? That's what we want to check out. So, I'll ask you guys the question, what are some possible outcomes? If two species are competing and having negative impacts on each other, what are some possible outcomes of that? Are you taking pictures of me?
I'm taking a video.
Of me?
Yeah.
Why?
Because, so I can look over this, because I'm confused.
I didn't even fix my hair this morning.
Oh.
I know. I zoomed into your head. You look nice and shiny.
Good, good.
Yeah.
Okay, so what are some possible outcomes? What can happen when two species compete? One of the species dies. So one out-competes the other one, and they go away. Or the opposite could happen. So species one could out-compete two, or two could out-compete one. What's another option?
Both die.
That's probably unlikely, but I guess it could be.
Yeah, I guess it kind of goes along with that. Just random circumstances make it so that a part of population 1 dies and a part of population 2 dies to
Okay?
equal carrying capacity.
But they're
in
both
that way.
still around.
But they're both still around.
So we call that coexistence.
Coexistence.
Yes. Rachel.
One of the species could adapt to live in another niche.
All right? We'll talk about that too. Although we're not going to talk about it with these equations, because these equations don't go that far. But that is a possibility also. Okay, so the three things really.
How would you change the equation to factor for maybe 8 different species that all consume the same resources in varying amounts?
You'd have to be really good at math and have a computer.
Well,
Do some modeling. I thought of that when I was in grad school. I was like, this is kind of bogus. This, just two species interactions going on. What if you did
This is
3
never the
species
case,
interactions?
almost.
what
Instead?
if you just throw
The math
shit in
was
there?
really hairy. Scared me away.
Sounds cool to
And then he
me.
became an
It
ecology
does. It's
teacher.
really cool,
Yeah.
but it's.
I like the way
intense.
things interact.
It's mathematically intense. Okay, so let's take a look at what these two things predict. So we're going to make some graphs that are called zero growth isocline graphs.
Nice
Zero growth isocline graphs. So zero growth isocline is a line that shows the population size of species 1 and of species 2 that would keep one of those species from growing. In other words, keep it at carrying capacity. So how many, if we were talking about species 1 here, carrying capacity 1, what are all the combinations of this number and this number that would make this add up to that? Okay? Because what's the growth rate when a population's at carrying capacity?
0.
0. So here the population could be below its carrying capacity, but when you factor this in together,
It's at carrying capacity.
they may be at carrying capacity.
Mm.
So a zero growth isocline represents all the numbers that would make this part of the equation equal to that. And then that would make this equal to 0. Okay, so that's why we call it zero growth isocline. So let's look at the possibilities here. So we're going to graph population 1 here. Population 2 there. We'll use a couple different colors. You want one to be green or red?
Green.
Alright. So one is green, species 2 is gonna be red.
Yeah.
There it is. Did you see how I calculated it in my head?
Whoa.
No, I just drew a line. But in order to draw a line, you only need to know 2 points on the line, right?
Yes.
That's the rule.
Yes.
So let's figure out the 2 points. So here, at this spot right here, n2 equals 0, right?
Mm.
So if we put n2 in here, this whole thing becomes 0. So what does this have to be in order to equal that?
All of it.
Equal to K.
K1. So this would be n1 equals K1. Right? Would be that point there. The other end of this is going to be when n1 equals 0.
N2 equals K2.
No, it doesn't work that way.
Okay.
Alpha, that's what it ends up equaling.
Wait. Could you explain what that value means again? Please?
It is, if you solve this, if you put a 0 in there, and you solve this, you get that. You'll just have to trust me. You trust me?
Yes, but I want to know why also, because I don't know.
We'll work on it this weekend, it'll keep you out of trouble. Work on rearranging that. Okay? Alright, alpha over K1. Or is it K1 over alpha? K1 over alpha. Alright, so you shouldn't have trusted me.
Alright, well,
Anything you know is a lie.
yeah.
How does alpha end up on the denominator? You're gonna have to divide it.
Somebody just open the door.
Right, what's this value gonna equal right here?
Why is there people outside?
K1 over alpha minus something.
So here we've got N2 equals what? K2, yes.
Yeah.
Oh.
Oh.
N1's at 0. Remember, bring a 0 in there.
Oh, I'm sorry.
Alright, so now this one. N1, what's it gonna be? Yeah, K2 over beta.
Are these supposed to be parallel lines?
They don't have to be. I tried to make them parallel, but they don't have to be.
Oh, okay. Just wondering.
It's just we're comparing essentially these two numbers, which is bigger, K2 over beta or K1. And here we're comparing which is bigger, K2 or K1 over alpha. Okay? So the answer to those questions will set up the way this looks. So the reason we call these zero growth isoclines is because along this red line, anywhere, any point on that red line means that this adds up to K2. So population growth is 0. Okay, so you have this many cottontail rabbits and this many jackrabbits. You're right there on the line. Okay? Alright, so what if the number of jackrabbits and cottontails is somewhere below this line?
Population,
Which population?
and first.
We're talking about the red line. What's the red line represent? Species 2, right? So this axis. So anywhere below this red line, and there's still carrying capacity left for population 2 to grow. If we're above the red line, then there is no carrying capacity left. They're beyond their carrying capacity, and population 2 would decline. We do the same thing for population 1. If they're below this line, so any combinations of population size N1 and N2 that's below the green line means there's still carrying capacity left for population 1 to grow. And if you get above the green line, population 1, species 1, will decline. You guys with me so far?
Yeah.
Wait, why are they going sideways?
Because the green represents growth or decline on this axis, N1. And the red represents growth or decline on this axis, N2. Okay, so the red line is the zero growth isocline for species 2, so they can grow up, they can grow down, and 1 can grow this way or that way. Okay, so now let's take a starting point. So let's say the population sizes of the 2 species is right there. Okay, there aren't very many jackrabbits and there aren't very many cottontails. So at that, under those conditions, at those 2 population sizes, what's the growth of each species doing?
Exponential?
Well, not necessarily exponential, but is it growing or declining?
It's growing.
Growing, okay? So that means that the size of N1 is going to be moving this way. The size of N2 is going to be moving up that way. Okay, so we'll just draw a line like this. We're going this way and we're going up. Both populations are growing. What happens when we hit that red line?
Growing stops.
For both?
No, the second species.
Just for N2, right? So N2, once we hit that, stops growing. Does population 1 stop growing?
No.
No. So now we move across like that. Now we're over the red line. So what happens to population 2? Starts to decline. And population 1? Still growing. So we're still going this way, but now we're going to be going down this way. Okay, so we're going to end up doing this and ending up right there. So in this scenario, the end game of this, the equilibrium point when everything becomes sort of stable, is just that population 1 hits its carrying capacity. And what happens to population 2?
Gone.
They're gone, okay?
Rip.
So this is what we call competitive exclusion. Okay, so this is competitive exclusion of species 2. Now what if the red line would have been higher than the green line? Then it'd be reversed. Then you'd have competitive exclusion of species 1, right? Your book will put it like this one right here. They'll say species 1 wins.
Yes.
either way you want to think about it, species one wins the competition or species two is excluded. The result is the same. Species two is gone, species one is there. If the two isoclines were reversed so that red was above green, then species two wins or species one is excluded. But next time, on Tuesday, we'll see what happens when we cross the beams.
Ooh.
You guys know what reference that's from?
So what?
Cross the beams?
Ghostbusters.
Ghostbusters!
Oh, okay, it's an extra question.
Cross the beams. Crazy things happen when you cross the beams.